Okay, let's start this seminar. This speaker is Mia West from the Durham University. She'll talk about Worst bubbles and doom, the cosmology of Higgs EFT. Please start when you're ready.
Thank you very much for having me. It's really exciting. So this is some work that I've been doing with my supervisor, Rodrigo Alonso, who gave a talk on HEFT or at school last year over Zoom. Juan and Rachel, who are postdocs, or they were postdocs at the IEEE. They've both moved now. Is it down?
Sorry. Here, restart. Let's try again.
Nice. Okay. Right, so the aims of my talk, what exactly is HEFT, Higgs effective field theory, and why should anyone care about it? What is the LHC not able to tell us about HEFT? Why are we looking at cosmology? So yeah, this point, and also some pheno that you should hopefully be able to see to do with HEFT. So yeah, I'll start with what is HEFT. I'm not sure how familiar everyone is with effective field theory, so I'll just do a quick overview. So essentially, you take the standard model to be the low energy effective field theory, and all new physics is at some very high energy scale, such that if you have, say, this 4-point interaction with a propagator that's this new physics at scale m big, then at much lower energies, it looks like a 4-point vertex with coupling that is 1 over m big squared. So this is basically exactly the same as Paul Fermi theory, which hopefully everyone's come across at some point. So essentially, it's taking these diagrams with lower point interactions and creating an effective vertex, which has a higher point interaction. Okay, so yeah, now we've got these effective higher point vertices. You can write down every 5-point vertex. So that's what these QIs dimension D do. So they sort of like these ones. And then you can write down what's called Wilson coefficients, which are how strong each of these couplings. And then this is all suppressed by this previous mass scale called lambda. And yeah, so these operators still obey the same symmetry group this time. So in standard model EFT, which is quite commonly used these days, we've got the electroweak symmetry with linearly realized. So SU2 left cross U1Y. The Higgs boson comes packaged in this doublet, which we can sort of rewrite as a radial type component and this angular type component. And then the potential is an analytic function of this staggered with itself. So in the Higgs effective field theory, the electroweak symmetry is not linearly realized anymore. So you get this SU3C cross U1EM. And it's actually the most general EFT parameterization of low energy physics involving the standard model degrees of freedom. So this is how the Higgs and the 3 Goldstone bosons come packaged. You can write all of these things in multiple different ways. These are just what I've used. So notice that this symmetry group is kind of like the broken symmetry of the standard model, and this is sort of unbroken. So essentially, HEFT isn't assuming anything about how symmetry is broken. Cool. So this is the HEFT Lagrangian. So we've got the Higgs, the kinetic piece of the Goldstone bosons. So this capital F of H, which is called the flare function. And you can write that as a Taylor series like this, with these coefficients A and B being arbitrary. Right. And yes, so this is how the Higgs couples to the W's and the Z's. And this is the tree level potential. So there's more stuff, obviously, that I'm not going to talk about in this talk, but there's certainly lots of interesting physics around there as well. So for the standard model case, this is the form of the flare function, and the Higgs can take on values from 0 to infinity because it sort of acts as a radius. So I'm going to try and talk about HEFT with some pictures, see how this goes. So essentially, the Goldstone bosons, you can rotate them using the, so what was O4 symmetry. So I'll take you back here. So this symmetry here essentially leaves the Goldstones rotationally invariant. We draw them in pictures. So basically using the fields, which are scalars, as coordinates. So yeah, essentially just as you would do with space, you can draw field space. Yeah, so you've got this symmetric axis for the Goldstone bosons, which you can rotate around freely. And the Goldstone bosons are completely symmetric around this axis. And then the Higgs boson sort of acts in the sort of radial direction, or as we'll see in HEFT theories that aren't SMEFT or the standard model, it's sort of, the word radial comes with a big asterisk. So these are some more manifolds that you can draw. So the standard model is this flat manifold. The so you can draw sort of spheres, cups with a sharp point, and then these sort of wormhole-y type manifolds. So basically anything as long as it's symmetric around this Goldstone direction, you can do that. So the question about so when you've drawn your manifold, you can classify your manifold into either SMEFT manifolds, or the standard model, of course, or HEFT manifolds, which aren't SMEFT, which we've called quotient theories. So the condition for whether you can do that is whether there's what's called an O4 invariant fixed point, or I guess O2 invariant, since I can't draw 4-dimensional pictures. Or I suppose it would be a 5-dimensional hypersurface. That's not good. Okay, so this essentially means that you need to have a point in which the manifold crosses the symmetric axis, and it has to cross smoothly. So the standard model has a point, this sphere, and this cup has a point. This does have a candidate point, but obviously it's a sharp, Right, yeah, so this is a sharp point, so it's not a O4 invariant fixed point. And this manifold here, excuse my bad drawing, but it basically doesn't touch the axis at all. I do have some backup slides which explain this in a little bit more detail and why you can draw HEFT theories in this way. So if anyone is interested in more information, please do ask. Okay.
So could you explain the correspondence between the standard model and the SMEFT? So as we know, when we take the decoupling limit, then the SMEFT it becomes a standard model.
Sure, sure.
So could you explain how we can understand by using the such geometrical objects?
Yeah, so for the sphere, I suppose it would be like squashing it. And then for this, also squashing. I think, so this is a very interesting question in terms of what does the limit of the, yeah, so how can you draw these in the limiting case? Specifically for this SMEFT, oh, I don't entirely remember, but I assume that there would be some dependence on the lambda parameter, and when you start taking that big, then the sphere would expand or something, or start to squash. I actually don't know which.
The curvature here, the curvature of this manifold correspond to the color scale of the theory, right? So standard model case, their color scale is infinity. So I mean, so it means that if the radius.
Oh, I see. So the radius
Yeah.
goes to infinity, and then the curvature
It
goes
disappear,
to
then
zero.
goes
So
to
then it goes. Thank you.
Could you remind me again about the quotient of the
Yes. So what would you like?
what's the quotient?
Okay. So quotient theory is a Heft theory that's not a SMEFT theory. So right. So Heft encompasses SMEFT, and that encompasses the standard model, of course. Yeah, so all of these manifolds are Heft theories, but only these ones can be described in terms of linearly transforming electroweak sector. These can't, so you need to use Heft for those pieces. Okay. So how can we look for a hole or a singularity in our manifold? So we've specifically focused on manifolds with holes in, so it doesn't go through this O2 symmetric axis. You can also refer to this paper for a look at what happens if there's a singularity. So essentially the problem is that we are at the vacuum, which is quite a distance away, a distance roughly v, so 246 GeV away from this O2 symmetric axis. And scattering experiments, so the LHC, you can calculate amplitudes like the W bosons going to Higgs. And because essentially you get the Taylor series in this effective field theory, you're only computing higher order terms in the Taylor series. And obviously at some point, you're not going to be able to measure a 10-point interaction at the LHC with any kind of precision. So we can only sort of find out the local curvature around the vacuum. So then how are we going to look for something like this? So we could just panic or give up, but too stubborn for that. So we're going to hope that cosmology can tell us something. Yeah, so I was previously planning to talk about some spalaron tunneling, but I haven't. But it should be in the paper, which will hopefully come out soon. Instead, I'm going to talk about vacuum evolution and the walls, bubbles, and doom that's in the title. So, as the lecture earlier talked about, so you can have this Tunneling, where the universe is in some sort of false vacuum and it tunnels to a true vacuum in little pockets called bubbles. And as it does that, so we start off from a point A on the manifold and we traverse to a point B. So essentially, we can look at some of this, like the global properties of the manifold, basically, rather than just local. So in order to do that, we need to build an effective potential from which we start at the tree level potential, which we've just taken the quartic HEFT potential. And then you need to modify it based on the temperature in the early universe, which modifies couplings, and then also include loop corrections. So first of all, the HEFT potential at tree level, the standard model and SMEFT, the Higgs boson is like a radial mode, in which case the potential kind of, so this is at high temperature, and of course as the temperature decreases, things change, but essentially you can only get, I think, SMEFT at dimension 6, certainly, and maybe even dimension 8. You can only get this sort of structure. But for a quotient theory, where you can have the Higgs not acting as a radial mode anymore, you can get mu minima, and then mu possibilities for tunneling. So the effective potential for a quotient theory, we've decided to essentially to get this extra range for the Higgs. You can do this by creating a wormhole manifold. So essentially you get the standard model flat manifold where the Higgs can go from 0 to infinity, and you sandwich it with another standard model like manifold where the Higgs is now going from 0 to minus infinity, and you create this. You create a little sort of portal between them, and now the Higgs can span from minus infinity to plus infinity. And then this is the form of the flare function that you get from this kind of manifold. So this beta is essentially controlling the width of this portal. Okay, so do keep in mind that by choosing a manifold, we've obviously restricted quotient space. So this phenomenology that we will talk about later isn't completely general to all Higgs effective field theories. But it's still illuminating to look at, so I will continue.
So excuse me, so is there any new physics model which can realize such geometrical objects? So
that is a really good question. Not that we have found, but we've found ways to get to, like, rather than being from, oh, wrong way. Yeah, rather than being from sort of minus infinity to infinity, you can get minus a bit to infinity. But yes, that is a good question. And
you found some renormalizable model which can realize such geometrical field combinations. So
no, essentially. So the best that we can do is something similar, but not the same.
you have not found the example?
No, unfortunately not.
Ah, okay.
But it is an active area of research that we're still looking into. But yeah, excellent question. I do have a backup slide which has the model that I spoke about where you can get a little bit negative, but not quite to minus infinity. So I can talk about that later. Okay, so in order to talk about an effective potential, we need to talk about some Higgs-dependent masses for starters. So you may have seen this effective potential at one loop earlier. I don't know if it's spoke. But essentially, this is the true level potential, and this is a modified propagator where you've got this Higgs-dependent mass term here. And so the details of this exactly don't super matter for this talk, but it's very interesting physics nonetheless. So we can extract these Higgs-dependent mass terms by taking the Lagrangian and then just looking for the coefficient of the massive pieces. So for example, the W and the Z, you just take two derivatives with respect to the W plus and W minus, and then you're left with the flare function times the normal mass. And for the Higgs, you just take two derivatives of the potential. We've also taken that the Higgs-dependent top mass is just the normal top mass times the flare function squared, but in a general case, this flare function need not be the same as this one. Unfortunately, it's not quite that simple because we want to compute everything in this on-shell gauge, and in that gauge, the W, so the longitudinal components of the W plus and minus and the Z get an additional contribution from the goldstones. So they don't appear in the heft potential, but they still impact things. So you get this additional component, which is related to this flare function. The top is completely unchanged, and the should put in the transverse components are as expected. Okay, so for a finite throat size for this sort of portal, the Higgs-dependent masses of the W and the Z and the top don't quite go to zero. They're still a finite sort of distance from zero. So that's interesting because in sort of terms of symmetry restoration at high temperature, these don't do that in the Higgs EFT. That's okay because the Higgs EFT is only valid up to a cutoff of temperature around 4 pi times the VEV. So that's okay, but it's still worth bearing in mind that there is no symmetry restoration in these types of theories at high temperature. I suppose that is to be expected, since for the Higgs effective field theory, we've chosen to essentially have already broken the theory before we build up the EFT, broken the standard model before building up the EFT. So this is what the loop corrections look like in the on-shell scheme. So we have this sort of form. The exact mathematics don't super matter, but this is what the corrections end up looking like. So for a boson, you end up with a sort of like a little cup. And then the fermions, you get a hat. So because of the shape, they don't super impact the phenomenology too much. They sort of change the heights of the false and true minima, but I won't mention them too much because they don't really change the overall structure of the theory. So these are the thermal corrections. So you sum over the W's, the Z's, the Higgs on the top. These are the most important contributions. And this is what the thermal corrections look like. They're sort of a cup. And as temperature decreases, the cup gets shallower, basically. So at low temperatures, obviously the thermal corrections don't make a huge difference. Yes, and so I kind of skipped over this extra parameter gamma A in the flare function, but essentially that changes where the thermal corrections lie with respect to the tree level potential. So you can see here, like depending on where exactly the thermal corrections are, changes the, will essentially change how the minima of the potential evolve as temperature changes. And so we've defined this new parameter called delta, which tells us which side of this local maxima the thermal corrections will be on at tree level. And so this is the functional form of what we've defined. This gamma E is a function of this parameter epsilon, which was a parameter in the potential. And this gamma 4 is also, I should have written the potential again, sorry. So this gamma 4 is the coefficient of the quartic term, and it's, yeah, so gamma 4 squared is the coefficient of the quartic term. Okay, so in total we have this effective potential, which is the tree potential, this quartic potential, one loop potential, and the thermal corrections. So where is this thermal potential valid? So there's this famous Linda's infrared problem, which basically says at high temperatures, the infrared bosonic modes become highly occupied. So essentially you get this effective expansion parameter for your thermal corrections, where if this Higgs dependent mass for the W and the Z become too small, then the effective expansion parameter blows up and you can no longer trust your effective potential. So what we've done to sort of deal with that is define this IR unsafe band, where we've essentially expanded this in terms of our quotient theory parameters. So this is a plot of the minimum evolution with temperature. So this is the high temperature, and this is what happens as it cools. And so this gray region is this IR unsafe band. So if this, so at high temperatures where the thermal corrections dominate, we just have this cup that we saw before. But as temperature starts to decrease, then more minima can show up because of the tree level potential. And essentially, if these new maxima and minima show up outside of this infrared safety band, then we have said that we can comment on this exact potential. If not, then we've chosen not to calculate anything. So people usually calculate this or deal with this infrared problem by computing daisy corrections. So essentially, you resum the most infrared divergent diagrams, which look like these little daisy things here, which depend on the, so yeah, you've got this scaling of temperature divided by this mass that was getting really small. And yeah, n is the number of sort of petals on your daisy. But this approach only alleviates the problem because you get all of these other diagrams, which will also start to blow up at some point. So you're saving yourself a little bit, but not totally. Also, if you start resumming things, then you end up with an inconsistent loop expansion. And also, so yeah, we're not a huge fan of this. Also, it turns out that in quotient theories, specifically the one that we were talking about before, the Higgs dependent masses can only get so small because of the finite throat width. And it turns out that most of the interesting stuff happens outside of this IR band anyway, so it's okay for us. There's another approach to dealing with the infrared unsafety, And this is called dimensional reduction, where you can dimensionally reduce your theory by integrating out temperatures, I believe. But that's hard, so this IR unsafe band was a lot simpler for us. Then also the UV cutoff that I've mentioned briefly before. So because we're working with an effective field theory, you can only take the value of the Higgs field to be so big, up to this 4 pi V star, which is roughly the normal Bev. And also you must keep the temperature to be below 4 pi V star as well. Otherwise you start breaking unitarity and such. And then finally, we've required that you have boundedness from below before this, this UV cutoff. And that comes from the fact that the top loop acting as this hat will sometimes create unbounded potential, effective potential. Cool. So I'll talk about how minima evolve in the quotient theories. So first of all, we've got this domain wall case in which the potential, the tree level potential, is very nearly symmetric around this point here. So it's almost exactly symmetric. And if you have a very, very small bias, so you can get a domain wall network like this forming in the early universe, but with a small bias, the domain wall network will evaporate, and then this leaves a phenomenological signal. So just a quick mention of this IR criterion. Walls don't have the same IR criterion, or we've decided they don't. Due to the fact that there's this very approximate symmetry, or almost exact symmetry in the wall potential. So in that case, you don't have to have the splitting of the sort of the minima be outside of this IR band. Yeah, okay. So this is the wall case, and then the bubbles and the doom case. So if this is how our potential is changing with temperature, so starting off with 1 minima, it splits into 2, and then, yeah, so today our potential is essentially the tree level potential plus the 1 loop corrections, but just sort of ignoring those for now. So if we define ourselves to be in this black blob today on the right-hand side, and then this black blob that you see is where the universe is mostly sitting. So this is the vacuum state of the universe. So if you see that as the universe cools, the thermal corrections put you to the right-hand side of the local maxima, you end up in this minima that we're in today, and then you stay in that minima that you're in today. So this is quite a boring case. No interesting phenomenology. The second case is the bubble case. So in this case, the thermal corrections put you in the left-hand side of this potential. So yeah, if this is the tree level potential, the thermal corrections is to the left-hand side of this sort of maxima. So the universe is in what was at this temperature the true minimum, but the true minimum then evolves into a false minimum, and then you can have this tunneling. And yeah, the tunneling, as we saw earlier, can lead to gravitational waves being produced. So it's some interesting phenomenology from this case. And then, yeah, here's the vacuum that we're in today. So there's a third case, which is the doom case, in which, so the thermal corrections go in the same direction as, oh no, Yeah, so the same direction as the boring case. So we end up in the true vacuum, which then evolves to be a false vacuum. And then at any time we could tunnel into what is the true vacuum. And this would be doom. So this is a quick summary of the parameter space and what kinds of potentials that you can have, and then the phenomenology. So along this x-axis is epsilon, which is a parameter in the potential that tells you about the height of the minima in the tree level potential. And then this delta is about where the thermal corrections sit. So this is the doomsday case. The walls are very close to the center of the axis, since you have to have a very small epsilon. And then this is the bubble case. Yeah, so you get the thermal corrections to the left of the local maxima. And so finally, the phenomenology. So for walls, we have this plot, which is quite complicated, so I'll go through it slowly. So we've got this log base 10 of the gamma 4 parameter, which tells us about how narrow or wide the potential is at tree level. And then again, this epsilon, which tells us about the height of the minima. So each of these bands tells us about the strength of the gravitational wave signal. I think this is the peak. And yeah, so this tells you, so these dashed lines here are the peak frequency of the gravitational wave signal. And this is, so yeah, this is, I should slow down a second. Okay, so and so this red blob here is an area that the gravitational waves could be visible at SKA. And this is another plot which shows the strength of the gravitational wave signal against the frequency. And these dashed lines are for some very small changes in the potential structure. This is a very old plot. I'm sorry, I maybe shouldn't have included it. Okay, but then if you add in the LHC bands, the plot from earlier just becomes this really tiny space up here. So actually SKA would never see any gravitational wave signal from the wall case, because there's only a tiny section that is actually visible. And so the doom case, the phenomenology of this would be the breaking apart of the world and everything we know. Fortunately, that's very unlikely to happen. So we've got this red region, which is all excluded by perturbativity. And so these solid lines on each of these plots basically where the probability of us decaying into a true vacuum from a false vacuum is 1. So essentially these are all way to the left of the perturbativity bounds. So we're pretty much okay. Then also there's this bubble case in the early universe where we have places, the universe is mostly in the false vacuum, and then small bubbles start to tunnel into the true vacuum. And in this case, little bubbles pop up. They start to grow and more bubbles are produced. And as the bubbles collide and produce sound waves, and there's turbulence from shocks in the plasma, then we end up with gravitational waves being produced. So quickly, the transition parameters. So this is the action for the tunneling, which you need to compute numerically for most cases. So we've done this using Cosmo transitions in any bubble, which you can download here. These archive will direct you to where you can download them from. And yeah, so the bubbles obey this equation of motion here, which is derived from the action, and then you can essentially calculate the action. And then the bubbles will essentially start springing up, and then when the action divided by the temperature is around 140, which is the case for an electroweak phase transition, then you end up with bubble nucleation. So this is essentially requiring that there's one bubble per Hubble volume in the universe on average. So essentially, you can get sort of nucleation happening before BBN if this criteria is satisfied. So if you remember this plot from before, this schematic plot, this is what happens if you put it into Cosmo transitions. So this blank area here is where the bubbles don't nucleate, so you never get to this action over temperature being 140. In this blank area here, essentially, you end up with the boring case. The boring case in which, very sorry, it's not the boring case. It's sort of an unphysical history. So we've defined ourselves today to be in this right-hand side vacuum. So this one, and in this unphysical history, we would be in this vacuum. So this is not happening. And then this area here, essentially we do get nucleation, and these are the bands for all the nucleation temperatures. So a lowered nucleation temperature usually means a stronger gravitational wave signal. So this is the really interesting area. So how do we compute a gravitational wave spectra for bubbles? You need to calculate some thermal parameters based on the action first. So you've got this alpha parameter, which is essentially the latent heat of the phase transition. So how much energy is released as the phase transition occurs. You've got this beta parameter, which is related to the duration of the phase transition. And then this wall velocity, which is how quickly the bubble walls grow. So this formula takes many assumptions. So ultimately, if you wanted to do a really solid calculation of the gravitational wave spectra in quotient theories, I would probably not use this formula, but we've just used this as a first approximation. So now what do the spectra look like? So the total signal is essentially a direct sum of the signal from sound waves and the signal from turbulence. The collisions also impact the strength of the signal, but not a whole lot compared to these first two. So we've neglected them in this case. So from the sound waves, you get this sort of hat-like spectra, and the turbulence case tends to be lower and more broad and also shifted to the right. And so usually experiments have sensitivity curves that go downwards sort of as a triangle, and you basically hope that your gravitational wave spectra, so this black dash line, overlaps with the sensitivity curve of the experiment that you're interested in. And if it does, then there's a chance that the experiment will be able to detect your gravitational wave. So for the case that I showed you earlier of the bubbles and the quotient theory, this is what the spectra looks like. So here we've got some common experiments, so LISA, BBO, BT, and SKA. And you can see that some of the ranges of epsilon, which I guess you can't super see through the some of the ranges of epsilon start to be visible at LISA and kind of BBO as well. So these are usually like these sorts of parameters, so between 0.038 and 0.042 are hopefully visible at LISA and BBO. Oh, if I messed up. Okay. So also we've got this complementarity with the LHC. So what does the LHC tell us about what values epsilon and delta can take? So using some recent ATLAS results, you can put these bounds on the amplitudes, and essentially you can translate those into a restriction for delta and a restriction for epsilon, and they look sort of like this. So yeah, delta on the y-axis and epsilon on the x-axis. And so we can put them all together in a summary plot. So this isn't super finalized because we're still making sure that all of our calculations are properly done. So take this with a pinch of salt, but this is roughly speaking what we would expect to see. So we've got this epsilon parameter on the x-axis, which tells us about the height of the minima, and delta on the y-axis, so where the thermal corrections go. Most of the parameter space has already been wiped out by LHC bounds. And then there's this small area just here, which we expect to be within LISA sensitivity for the calculation that we've done, obviously including the approximations that we've used. So yes, and obviously on this axis here, we've got the latent heat of the phase transition. So you could also put the nucleation temperature on this axis as well. But yeah, so greater latent heat is also associated, generally speaking, with with the peak of this sort of spectra being higher, and also around this point, lower latent heats tend to be so spectra that are lower down and therefore not visible at these experiments. Okay, so conclusion. I'm not entirely sure. Okay, yeah, so conclusions. There's this increasingly pertinent question. So which EFT should we be using to describe nature? So is it the SMEFT, or should we do our calculations in terms of HEFT? So SMEFT obviously has the advantage that it has a much less great set of parameters for your fittings, for example, whereas HEFT has loads and loads of parameters. So it's quite tricky to persuade people that HEFT is useful. But yeah, of course, SMEFT couldn't tell us about things such as strange goings on in the manifolds. So yeah, it is indeed possible that cosmology could tell us a little bit about the global properties of quotient theories through these gravitational wave spectra, and bubbles seem to be more promising than the Wall case, and definitely better than the Doom case. So finally, just some outlooks. from this work and also some interesting questions. So what happens when you take beta to be really small? If you take beta to be really small, then you end up with this like strange spike in your thermal corrections and your one loop corrections, which obviously makes tunneling more difficult since there's this huge spike, but it'd be really interesting to see if anything else interesting happens in this case. Also, if you take beta to be ever smaller and you take the standard model limit, then you end up with this spike being sort of more and more prominent. So how does that reconcile itself with the standard model limit? That is a really interesting question. So this question from before, what sort of UV physics could give this wormhole manifold? What happens if you include more terms in your tree level potential? Say rather than a quartic potential, you could start adding 5 Higgs, 6 Higgs, etc. What would that do for, say, multi-step transitions where you have multiple phase transitions happening? And also, what if you change this flare function and use a different manifold? What happens then? And also, what happens when you make the boson and the fermion flare functions different? So that's everything I wanted to say. Thank you very much.
Thank you very much for the nice talk. Any question?
So could you show me the prediction of the gravitational waves?
Yeah, sure. Would you like this one or this one?
Yes, it's fine. So I thought that the prediction of gravitational waves are very similar to the prediction in several extended Higgs model. So,
Sure.
can you distinguish your scenario and the other renormalizable model? So
This is
how
a
do
very
you
good question. So the short answer is no. The long answer is one would maybe be able to use this as an indication for perhaps I don't know. So it would be similar to measuring, say, a resonance at the LHC. What exactly caused it, you don't know. I guess this would be a very similar case in terms of you get a gravitational wave signal. What is it? So if you did measure a signal like this, it could be from many different things. Perhaps the fact that it's a signal from an effective field theory is quite helpful in terms of it would be classifying a range of other theories that would come under the quotient theory umbrella. But nonetheless, you've made many assumptions to get to this EFT anyway. So yeah, it is indeed a really good question.
Yeah. So the line, the spectra,
Yes.
bottom one, why does it have 3 peak?
So that is a very good question. I think this one is from the sound waves, and then this is from the turbulence. So the trouble with the gravitational wave spectra, as it's currently understood, sound waves are very well understood.
Yeah.
Turbulence, not so much. So
your spectra is the sum of sound waves and turbulence. Right?
yes, this thing.
So I would understand that one peak is coming from sound waves, and the other one is come from the turbulence.
Yeah.
So there should be.
So this S, capital S here, is a sort of yeah. So this is where the frequency dependence mostly comes in, and that's calculated with
So that would
lattice,
do
I
like
believe.
this
Yes.
peak or maroon line, right?
So I think when you get to higher frequencies, this can create extra peaks as far as what this is currently understood to be, but it does look weird, and
Yeah, I think the middle peak is the sound wave. Go to the next slide. I think the middle one is sound wave.
Oh, this one.
Yeah, I think so. That's the dominant.
That's a good. I can. So my collaborator Rachel made this plot, so I can ask if she can
Okay.
split them. If that would be. So that's actually quite an interesting question. It does look strange.
Any other question?
What is omega h square maximum?
Is what? Sorry, the.
The omega h square maximum dotted line.
Okay. So that is. Sorry. So within, say, this pink range, what's plotted as the dotted line is the maximum gravitational wave signal that you can get. So that's like the highest within each range.
So what you are showing is that for each epsilon range,
Yes. What's
solid line and the dotted lines which overlaps. No?
yeah, they all overlap. So
It's not. It's always overlap. I mean,
yeah. Sorry, I forgot that this
I
is how it
think
would be plotted.
the H square omega max is the peak point, and then for each point you can draw a spectral line.
yeah.
So I think the solid line and the dashed line both are drawn for the peak point, but I think in that range you can have other solid line as well.
Yes, exactly. Yeah, sorry, I should have made that clear.
Could you show the slide which define epsilon and delta again?
So okay, so I apologize. I definitely should have written the potential further on in the talk as well. So this is this
Yeah.
epsilon parameter, which shows up in the tree level potential. And that, yeah, tells you about the height of the two minima. And delta is defined a little bit later on. Yes, so here. So this is delta. So this gamma epsilon is a function of epsilon, and essentially it's supposed to be yeah, whichever sign of delta is telling you about which side of the local maxima.
So this quantity epsilon and delta are well defined only in Higgs EFT, but not in SMEFT.
So doing a direct comparison is okay. Maybe I'll go back again. So in the standard model EFT, because in the early universe you have symmetry restoration, the thermal corrections will always take you to this point here. Yeah, where the Higgs is 0. And so when you get tunneling out of that vacuum, it's always in this direction. So delta isn't as super useful, or isn't as useful in the standard model EFT, but it's very useful in this quotient theories because it's important as to essentially wherever the minima of the thermal corrections are, is where the universe will sit at high temperatures. And then as the temperature begins to decrease, you get more minima showing up. So from this tree level potential. So you need to, essentially, if the thermal corrections put you here on this plot, then you can have tunneling. if the thermal corrections put you here, then you don't get anything. So it's super useful to have defined delta in the quotient theory case. But in the SMEFT case, it's quite different.
Can you show the slide which define FH, capital FH?
Yeah, of course. What was that? This one.
The earlier one.
Oh, okay.
The
The
Lagrange.
Lagrangian, this one.
Yeah. So FH is in principle so infinite number. I mean, infinite number of powers of H over V.
Exactly.
So do you define FH just keeping the first one or two terms, or you are including everything?
So for this phenomenology case,
Yeah.
what we've done is define. So we've chosen a manifold, this sort of wormhole type thing,
Yeah.
and that gives you a capital F of H, which works for. So that works for all.
You assume there is some FH which gives you quotient manifold looks like a formal.
Yes, exactly.
But you don't know what will be underlying UVC with that will.
Exactly. Yes. So we have some ideas. So we spoke to Dave Sutherland, who has worked quite extensively on talking about manifolds and things, and he had some ideas. So this is something that we're going to be looking at as to whether you can find some UV physics which gives you a wormhole-ish manifold. So yeah. Oh, I've gone in a terrible direction. Yeah. These kinds of manifolds are easier to find. The wormhole type, not so much.
Take this wormhole shape manifold because you don't want to take some manifold that has some meaning to the standard of the EFT.
Yes, exactly. So the main reason that we want to have this wormhole manifold is because you can extend the range of the Higgs, so what the Higgs scalar can take as its values, from being like in the standard model or the standard model EFT to be some sort of radial mode, so you can only go from 0 to infinity, to using this wormhole type setup, you can get the range of the Higgs being anything. So that's the main reason, because you just want to expand what range the Higgs can take, which then allows you to use those sort of quartic potentials with different minima and different minima evolution.
Further question?
In your model, so you introduce the form of the capital F. And then so the expression of the field-dependent mass of the gauge field can be changed.
Yes.
So is there any constraint from the oblique parameters, like especially the low parameters? So
The which parameter, sorry?
the low parameters. Low parameters. So the oblique parameters, so STU or STU parameter. So,
Sorry, I'm not sure I've understood. Can we talk about it later?
If not, let's thank speaker again. Thank you very much.